Hello, good evening everyone. I welcome all of you to Gradeup channel of YouTube. Hello, good evening everyone. I welcome everyone to the Gradeup channel. All of you please join together for today's session, which is on bending stress and shear stress. Am I audible to all of you? Hello, praise. Good evening. So very good evening to everyone. Am I audible to all of you? Yes, this lecture is going on in a champion study plan. It is your champion study plan which is already going on from past so many days. It is 120 days plan where you are getting all the practice and theoretical ones. So theoretical will be conducted in your app, Gradeup app at 11 a.m. and the practice session is going on in a YouTube. Hello Santosh, good evening. Hello Sambita. Okay, so let us start now. All of you please join fast. So this is my small brief introduction, and here is your Vision 2002 and 2023 both Hindi and English batches are there. Texts are lagging. Okay, what kind of lagging in text? So these batches are going on. You can join that batch. These are the star faculty of the Gradeup, and there is that great 2022 champion study plan. This champion study plan is for 120 days. If you want to get the benefit from a champion study plan, you should go there in your description box. So go to the description box and see the schedule. In a schedule, if you'll see, you will find notes as well as theoretical. Wherever the theoretical is given, that at 11 a.m. that lecture also will be there. At the same time, you'll find the practice session. So go to that particular schedule given in the description box. Then there's a mega mock challenge on 29th of August for bar. Please join there. Now here's the first question for you from Bending. So all of you please share it once, share it with your friends, and do not forget to like also. The assumptions in the theory of bending. Please share it. What will be the correct option here? Yes, it is D. Okay, so this is very basic question. Those who have actually studied bending, this is the first question will be asked, and very basic question, right? So the assumption in the theory of bending, material must be homogeneous, doesn't it? Metal must be homogeneous, isotropic. Young's modulus is same in all the tension as well as compression. All the options are correct. That's all. Pick up the correct statement from the following. The bending stress in a section is 0 at its neutral axis and maximum at the outer fiber. The shear stress is 0 at the outer fiber and maximum at the neutral axis. The bending stress at the outer fiber is known as the principal stress. Which one is correct here? What will be the correct option here? The bending stress in a section is 0 at its neutral axis and maximum at outer fiber. The shear stress is 0 at the outer fiber. Now if you see here carefully, the bending stress, yes, the first statement is correct. At neutral axis, the variation of the bending stress, as you know, at neutral axis you have 0. The shear stress is 0 at the outer fiber and maximum at the neutral axis. That is also correct. If you see the across the depth of, suppose this is your beam, across the depth, if you'll see the in rectangular beam, the variation of the shear stress is parabolic and it is 0 at outer fiber and maximum at neutral axis. That is also correct. The bending stress at the outer fiber is known as principal stress. Why? Because see, on outer fiber, if you do not have shear, on outer fiber, if you will consider the element from the outer fiber, just you consider the element, take out any of the element from the top. What is there on the top of the element? Either, so the state of stress, if you will see here on the top of the element, either it will be having compression or tension based on the bending. Suppose now downward loading, it will be having a compression but no shear. So the plane without the plane where normal stresses are acting without shear, if the shear stress is 0, you know that plane will be called it as principal plane, isn't it? And the stresses which are acting there will be known as principal stress. So yes, of course, at the outer fiber, either top or bottom, at the outer fiber, the bending stress will be called it as the principal stress only. Did you get that? So here also all are correct. Next one, which of the statement implement the plane section remains plane assumption in the theory of bending? The stress varies linearly across the depth. Strain varies linearly across the depth. None or both A and B. Which of the option will be correct here? Which of the statement implement the plane section remains plane? Here, as you know, the plane section remains plane, that is Euler-Bernoulli's beam. Plane section remains plane. Actually, it implements the variation of the strain. Implementation of the plane section remain planes, it gives you the variation of strain. Strain varies linearly due to that, right? The strain across the depth varies linearly. It varies linearly. But now if you are implementing once again the Hooke's law along with that Euler-Bernoulli's beam assumption, then only we will write that yes, stress will vary. As you know that stress is proportional to strain. So variation of the stress across the depth, linear, is not only due to the Bernoulli's beam theory or assumption, right? It is along with that. If you will implement the Hooke's law, then only you will get that. So if it is about plane section remains plane assumption, yes, it is a strain which varies linearly across the depth. The stress, one cannot say that until or unless you are not adding Hooke's law together with the assumption. Did you get that? So correct answer will be B. Derive the dimensions of a strongest rectangular beam from a wooden circular log of diameter D, which can have maximum moment of resistance. What will be the maximum moment of resistance here? Maximum moment of resistance. So moment of resistance, you know that if you have a circular log, that is wooden log. Now in a circular log, he is asking that what dimension I should take, which will give me the maximum moment of resistance. While taking out the section from circular log, what must be the dimension, right? Suppose this is B and this is yes, you can take it as maybe small d. Yes, small d. What dimension I should take? Because lot of different sections can be taken out from that particular circular log. See, if you will think about about the strength or moment of resistance is nothing but your permissible value of the stress multiplied by Z, isn't it? Sigma permissible, whatever it is permissible, into Z. Now this Z value actually is section modulus. It depends on the section modulus. So from the same material, if you are taking out, so actually you want to compare a different sections which you can take out. Maybe one can take out like this also. I'm just considering the two sections for your understanding. It is about B by D. This is your B and this is your D. Now actually which one you should take where you will find the maximum moment of resistance? Indirectly, where you will get the maximum section modulus, because the permissible sigma is same for all the material. As you are using the same material, your sigma permissible is constant. So yes, to get the maximum you should get the maximum Z. Now you know that what is the section modulus. Section modulus is BD square by 6 for the rectangular one. Now I'll write down that BD square by 6. If you see that from the perspective of the maximum, if you differentiate with respect to what? You have two variables, that is B, the width as well as the depth. Now here you implement one idea which you can see. Either you consider this section or maybe you consider the another one. The common point, if you see here, is your diagonal. The diagonal is constant every time. So what we can do, keep it one relation here. The diagonal square is nothing but B square plus D square. That is sure. B and D may vary, but diagonal will be constant whatever the section you are taking out from that circular log. So just D square, you just keep it there in the place of D square. Just again. Okay. Now Z will become how much? B, just in the place of D square, keep it D square minus B square. So that is B into D square minus B square divided by 6. If you see carefully here, now Z is your section modulus. You want maximum. So what you will do? dz by with respect to B. Now B is the only variable quantity here, must be equal to 0. Do that partially, sorry, you differentiate it with respect to B. If you differentiate, what you will get here? That is D square by 6 minus, sorry, 3b b cube. So 3b square by 6 equals to 0, and here you will get B equals to D by root 3. Keep that value here, so you will get D equals to under root 2 by 3 of D. That's all. If you have any doubt, please let me know. That's all. Keep the value B at this location in this equation, sorry, maybe equation 1, and you'll get the value of D. Remember, whenever you are thinking of, see, you can take out any of the section. Actually you are worried about maximum moment of resistance, and the maximum moment of resistance, now actually you are worried about maximum section modulus. Section modulus can be compared for a same type of material. If sigma P, the permissible stress for a material, is constant, one can compare the section modulus to get the maximum strength. Is it clear? Is it clear to all of you? Okay. The ratio of the length and depth. The ratio of the length and depth of a simply supported rectangular beam which experience maximum bending stress equal to tensile stress due to same load at its midspan is. What will be the answer? Which one is correct here? Okay, so here this is also quite simple, isn't it? He's asking that if you have a central, if a beam is loaded centrally, then what is the ratio of L by D? Simply supported. Okay, so now you have a simply supported beam and a centrally loaded one. So ratio of length and depth simply supported rectangular beam which experiences maximum bending stress equal to the tensile stress due to the same load. Now maximum, what is the maximum bending stress? What is the maximum bending stress? Tell me, what is the maximum bending stress? So maximum bending stress experiences, so W if it is here, what is the maximum bending moment here? If it is W, the maximum bending moment is simply it is W by 2, it is W by 2, है now maximum bending moment is WL by 4. If maximum bending moment is WL by 4, what will be maximum bending stress? So bending stress is nothing but M by Z, isn't it? M by Z. Just now I have written M, already I have written that WL by 4, so it is WL by 4 into that Z is BD square by 6, so 6 by BD square, isn't it? 6 by BD square, and it will become how much? 6 by 4 WL by BD square. That is your maximum bending stress. Now maximum tensile stress. Maximum tensile stress due to the same load. Due to the same load, the maximum tensile stress will be what? W by BD square. That's BD's. That's all. W by BD. That is the maximum tensile stress. Must be equal to 6 by 4 of WL by BD square. Now WW will get cancelled and BB will get cancelled. L by D will become 4 by 6, or I should say, see here, that L by D will become 4 by 6, or I should say 2 by 3. That's all. That's what he was asking about. That is what he was asking about. It is not A, it is option B. Did you get that? If you have any doubt, please let me know. Please let me know if you have any doubt here. Are you able to understand this? A simple supported beam of uniform strength along the span of L carries a point load W at mid span. If the width of beam is constant, okay, width of beam is constant, and the permissible stress in bending is throughout the length, and the permissible stress in bending is throughout the length, okay, throughout the length, then the depth of beam at a distance x from the support will be maximum tensile. Okay, I will explain. Can you understand this one? Maximum tensile means just first of all you understand, those who are just read this question. Maximum tensile means you just apply, this is your, you apply the W here. Suppose this side is fixed, apply W. What is the maximum tensile? W by cross section, that's all. That is the maximum tensile stress. Maximum tensile stress. Now this question is quite interesting. What he's saying that you have a beam and the beam has a constant width. Read out very carefully. And the beam has a constant width, right? Okay, beam has a constant, where is it written? Width of the beam is constant. Can you see that? For the constant width of the beam, okay, maybe, okay, the depth has not been said, anything else, so just constant width of the beam, right? And he's saying that what, this is, I'm talking about, this is the width, this is no more depth, right? Point load W acting at a midspan, okay, at midspan, and W is acting, length is given L, then pervasive stress in bending is throughout the length. Okay, that's very nice. Understand this question carefully. First of all, what he's trying to say here, what will be the bending moment diagram? The bending moment diagram due to the applied load will be simply this one, right? If I'll ask you, what is the moment of resistance of the beam? The moment of resistance, if you have a continuously throughout same cross section, the depth, if you have constant throughout the beam depth, what is the moment of resistance? The moment of resistance will be calculated based on what? Moment of resistance is nothing but, what is that? Tell me. Sigma permissible into Z, that BD square by 6, isn't it? I will write down that directly. It is nothing but BD square by 6. Now if I am saying that B is constant, if you will keep the D also constant, throughout a constant moment of resistance you will find. Throughout a constant moment of resistance you will get. This is too big, I have drawn. Just a moment, I'll just make it smaller one. Are you getting my point? Now when you are designing the beam, what will happen? You are designing it for the maximum bending moment. Suppose this is your maximum bending moment. So for the maximum bending moment, if you design, of course you will provide the, suppose if you are keeping the constant width throughout, what is the moment of resistance you have? This is the diagram for moment of resistance. Suppose the red one, the black one is the requirement of bending moment. This is the bending moment all across the beam. All across the beam you have a bending moment here. If I'll ask you what is the bending moment, this is the bending moment. What is the bending moment due to load? These are the bending moment due to the applied load. If I'll ask you what is the moment of resistance available in the beam, the moment of resistance available in the beam are quite larger than that at every place, other than only at the central position. The moment of resistance everywhere is this much. Are you getting my point? Moment of resistance. Now actually this is almost, I should say, is it waste almost kind of thing, because this is not required. This is not required. So sometimes, now understand it, he is saying that if the width is constant, now what must be the depth? What must be the depth? Because here that much depth, constant depth of D is not required. The depth D, whatever is required here, it is not required. It is less than that which you need here. So kind of a variation will be needed here. Are you getting my point? Kind of a variation in the depth will be needed. Now what he is asking, a maximum depth D is not required at every position. So can you tell me what will be the depth at some distance x? At some distance x, if I want to know what is the depth, can you tell me what will be the depth here? So let us consider what must be the depth at that location. So equate your moment of resistance with your applied your moment. Now W is the load. Here you will be getting reaction, that is W by 2, and here also you will be getting reaction W by 2. The bending moment at the section, bending moment at this section will be what? W by 2 into X. That is the bending moment you have. That must be equal to the moment of resistance. Now moment of resistance, you already know that sigma permissible in the bending multiplied by B D square. That D I don't know at all, by 6. Now B you consider as a unit weight because he has not said anything and it is not given here. Maybe sigma B is in multiplication, I think, or if it is given, that B, I think it has come in suffix, it must be, or B, if it is not given, consider as a unit weight, no problem, right? Then he's asking about depth. So dx will become how much? 2 3 just 6, it is 3wx divided by sigma permissible into B under root. That is the depth you will get at section x, at distance x, depth of the beam. Are you getting it? Depth of the beam, that is what it was asking. Now if you see, that is why you, first of all he said that width is constant. If width is constant, then only we are varying depth accordingly. It is easy to calculate depth at any position. Are you getting my point? So if width, width you take it 1, then 3wx by sigma permissible, C will be the correct answer. If you have any doubt, please let me know. If you have any doubt, please let me know. Okay. Find the ratio of moment of resistance of a square beam when placed with horizontal and vertical sides to the same beam placed with the horizontal and vertical diagonal. So once you are placing it like this, and once you are placing, what is the meaning of that? Actually, once you are placing your beam, moment of resistance, once you are keeping your beam like this, and at the next instant, then this is your axis about which it is going to bend. Maybe this is the axis about which it is going to bend, and another time you are keeping it right? Now this time your bending will occur about this axis, about this axis. This is your position of the beam. Now who is asking? He's asking simply what is the moment of resistance, ratio of the moment of resistance. What will be the ratio of the moment of resistance? What will be the ratio of moment of resistance here? So now moment of resistance for this one and this one. If you see, first of all, if it is a square section, if it is a square section, for the square section, first of all, for the square section, the moment of inertia will be same about any of the axis. Moment of inertia. So I can write it down. That is simply A4 by 12. Moment of inertia is same about all axes. Now what I will do, moment of resistance is what? Moment of resistance is simply, moment of resistance is what? Sigma permissible multiplied by sigma permissible multiplied by Z, or I should write down I by Y max. Y max. The what is Y max? The distance from the neutral axis to the outermost fiber, isn't it? Outermost fiber. Here it will be A by 2. And here if A is the side, what will be the extreme most fiber distance from the neutral axis? What will be the extreme most fiber from the neutral axis? So this distance will become how much? Can you tell me? This distance will be, you calculate it. This is your A and this is your A, and this is also A. If you extend it here, the final total depth, total this distance will be how much? A square plus A square under root, isn't it? That is A square plus A square under root. I should say A root 2. The diagonal is A root 2 divided by 2 will give you the half of that, divided by 2. So it will become how much? A by root 2. A by root 2. That's all. Now write it down the moment of resistance for both of them. Write it down the moment of resistance for both of them, isn't it? So while writing down the moment of resistance, okay, here you go. Here now you can see that the moment of resistance, if you write it down, moment of resistance may be due to 1 by moment of resistance due to 2. What I can here, moment of resistance due to 1 by 2. Sigma permissible will get cancelled, and simply Y max is in the denominator. So Y max due to second one will be at top and Y max due to 1 will be at the bottom. That's all. That's all. Then Y max for the 2 is simply A by root 2, and for the first one is, suppose this is the first one, this is the second figure. So in second situation, so this is simply A by 2. Finally what you will get? What will you get? A will get cancelled and you will get 2 by root 2, that is nothing but root 2. That's all. Did you get that? Can you solve this one? How to solve this one? A beam with a cross section given below is subjected to a positive bending moment causing compression at the top of 16 kilonewton meter acting around the horizontal axis. The tensile force acting on the hashed area of the cross section. What is the tensile force acting on the hashed area? Here if you see carefully, a bending moment is acting, that is 16 kilonewton meter, right? Acha, you know that for the rectangular cross section, if this is the width of this is the cross section of the beam, you know that the bending stress beam cross section is not subject to positive bend. So bending moment, variation of the bending stress, the variation of the bending stress across the width of the beam. This is your beam. This is your depth of the beam. So across the depth, the variation will be suppose from acting 16 kilonewton meter. 16 kilonewton meter. This is the variation. Suppose here you have a neutral axis, maybe that is at mid of the beam. It is a symmetrical one, right? Now this is the stress which will vary. which will vary across the depth. He is asking what is this is the stress variation. This is your bending stress variation. Stress, simply this is stress, bending stress. Now he's asking what is the force in that hashed area. So the problem is that the force calculation, how you'll do that, because here there is a variation. See, area you can calculate 25 into that 50, that will give you the total hashed area, but area must be multiplied with the stress, will give you the total force. Problem is that the stress is varying here. Actually, I will just draw the another diagram for your more understanding. How it is varying, and what exactly you have to calculate. I'll just take a few moments, right? This is your rectangular beam, right? This is your now across the depth, this is your rectangular beam, and this is the position of your neutral axis. Now from the neutral axis till this position, your stress will be varying. Actually at neutral axis you have a 0, but from the neutral axis, if you'll see, from the neutral axis it will vary, and you'll be having some values here. Just try to see that, and the value will be how it will vary. Some at some depth, maybe at this location I'm talking about, at this depth, what is the stress level at this depth? It will be having some value, right? And the variation will be are you able to understand that? This is the stress variation across the depth here. This is the stress variation across the depth here. Are you able to understand that? And once you know there is a variation, it is now important for you to calculate. So how you will calculate? You know the area. Which area I'm talking about? The area, this hashed area. If you know the area here, the hashed area multiplied by the stress. Which stress you will consider? If you stand and if you see from here, that's what you are seeing it. This is the portion you are able to see. This is the portion you are able to observe if you are standing here and observing. Now how you will calculate? Just simply consider the average. One, that's all. So consider the average stress. So first of all, here the bending stress at this position is 0. What is the bending stress at this position, at this depth? That you need to calculate. So depth is known to you 25 mm. Then you calculate the bending stress. The bending stress will be simply how much? M by I into Y. I, if you calculate, I also must be calculated. Okay, I'll calculate first of all I'll calculate I here. So I will be how much? BDQ by 12. So that BDQ by 12 here, write down B is how much? B is 50 plus 50, that is 100, isn't it? You consider that 100 maybe in terms of centimeter will take. B, the depth is how much? 75 150, so 15 cube, BDQ by 12. You will get some I value. Then that I value you use it and calculate sigma, that is M by I into Y. That Y is the depth which you know. What is that depth? So M by I 16 kilonewton meter divided by 0. If you change it to meter also, this one you change it in terms of meter raised to 4, then you will get find almost 0.281 into 10 raised to minus 5. That is the moment of inertia which you will be getting after calculation in terms of meter. Although I have given, you just take it in meter, better you take it in meter. So 0.1 into 0.15 q divided by 12, and you'll get 0.281 into 10 raised to minus 5 multiplied by Y. What is the value of Y here? You are interested to calculate bending stress at this level, which is at 25. So just 0.025 in terms of meter. If you'll calculate the bending stress you will get almost some value. And now once you have calculated the bending stress, what you'll do, you have to calculate the force will be 0 at this location, and bending stress at this location, whatever you're getting, that 0 plus sigma divided by 2. This is not 6, this is sigma divided by 2. That bending stress multiplied by the area, multiplied by the hatched area. If you see the hatched area, simply 0.025 multiplied by 0.05 in terms of meter if you are talking about, right? 0 plus sigma value what you are getting, and finally if you calculate all together, you'll find 8.9 kilonewton, right? That do the calculation, perform the. So first of all, it is very much important, you should understand it carefully what is happening here. A beam of square section, cross section is used. Can you solve this one? A beam of square cross section is used as a beam with one diagonal as horizontal. The location of the maximum shear stress. Oh, now this is from shear stress. The location of the maximum shear stress from the neutral axis will be. Okay, if you have a beam, what will be the answer for this one? This is quite easy. This is quite easy. A beam of square cross section is used as a beam with one diagonal horizontal. Okay, if you want to keep one diagonal as a horizontal one, what will happen? It will be your, if you will keep one diagonal as a horizontal, then you'll get this shape, isn't it? Then he's asking what is the location of maximum shear. What is the location of maximum shear? So for those things, actually it is better you remember it. What is the shear stress variation for this type of cross section? 0 at extreme fiber, as it is coming here, actually maximum area at mid, so it will actually reduce, then once again it will increase, and once again it will become 0, right? Now from the neutral axis is asking what is the maximum shear stress. So maximum shear stress, this distance is asking, this distance, right? This distance, you please do remember, this is actually b by root 2, b by root 2. The total actually, if this is the bit b, what is this one? B root 2 by root 2. So actually it is b by root 2. So b by root 2 you need to calculate. Why? Because, sorry, b by 4. Here this distance is b by 4. B by 4. Whatever it is, b divided by 4. Now this distance, how you will calculate here? Because if this is b, what is this height? This will become what? B by root 2. So simply b by root 2 divided by 4, b by root 2 divided by 4, and you will get b by 4 root 2. B by 4 root 2. So this distance is actually this height divided by 4. H divided by 4. I should write down h divided by 4. So that h actually you have now b by root 2 divided by 4, right? B by root 2 divided by 4. In the beam of solid circular cross section, what is the ratio of maximum shear to the average shear? See, if it is circular or triangular or rectangular, whatever, actually you need to remember for that one, right? Although it is a solid circular section, but remember it, it is very much helpful. For the circular section, what is the variation? Variation is like this. He's asking what is the ratio of maximum shear stress to the average shear stress. The average shear stress, the average shear stress, already you know that simply average shear stress is what? Simply divided by total cross sectional area, right? So here tau max, the tau max is nothing but 4 by 3 of tau average. 4 by 3 of tau average. So he's asking what is the ratio of maximum to average. Maximum to average will become 4 by 3. Remember for all of them. A timber beam is 100 mm wide and 150 mm deep. The beam is simply supported and carries a central concentrated load W. If the maximum stress in the shear is 2 Newton per mm square, what would be the corresponding load W on the beam? What would be the corresponding load W on the beam? Hmm? Any comment? No. What will be the? This is quite easy. Can you calculate that? So timber of width 100 and width 100 mm and 150 mm deep. The beam is simply supported and carries a central constant load. The maximum stress in the shear is 2 Newton per mm square. Now, the maximum stress is 2 Newton per mm square. You know that tau max in the rectangular one is 2 by 3 of, sorry, 3 by 1.5, na? 3 by 2 of tau average. That's what we know. Now, tau average is quite easy to calculate. Simply all together, whatever the shear force you have divided by total area, isn't it? Shear force by total area. So, tau max already given. The maximum shear stress is 2 Newton per mm square. 2 Newton per mm square. Must be 2 by 3, you take it here. 2 by 3, you bring it here. Then equals to tau average. That is whatever the shear force you have, that shear force divided by area is B into D. B into D also you write down. Area is what? B. Width of the beam given as 100 mm. So consider that I have taken mm row. Mm. So you take it 100 mm into 150 to get that. 100 into 150. What you will get exactly here? S equals to 4 by 3 कितना हो जाएगा 4 by 3 into 100 into 150 तो 3 5 15 5 20 20 और 0 1 2 3 1 2 3 200 किलोमीटर राइट 20 1 2 3 4 1 2 3 4 so 20 kilometer, that's all. 20 kilometer. Okay, A, you got it right, Santu. A cross section of simply supported beam is as shown in figure. The shape of shear stress distribution across the depth will be the shape of shear stress distribution across the depth will be, what will be the shape of shear stress distribution? B 100 Santu. Yes, it is B. See, as you know that area increases, area sudden increment of the area, so sudden decrement of the stress, that's all. Parabolic variation, and as area increases sudden decrement, once again it will be parabolic. So difference between the B and C, if you see here, the variation in between this portion is no variation, it is constant, which is not correct, right? The variation, parabolic variations will be there. Now once again a sudden change and you'll get this. Absolutely correct. This is not correct. Okay. What about this one? A beam with a rectangular section is subjected to shear force. F at a section. Then shear force resisted by upper 1/3 section will be. Upper 1/3. Matlab, suppose this is your rectangular portion. So rectangular beam is asking the shear force resisted by upper 1/3. So upper 1/3 matlab 0 to d by 3, that's all. 0, this is d at d by 3, maybe from top. Upper 1/3 by this. What is the, maybe this is neutral axis. What is the force resisted by, shear force resisted by upper 1/3? You know that there is a variation, right? Across the depth there is a parabolic variation. Now once again I'll say the same thing. If someone will ask you what is the force resisted, so if you will give me the, see here it is quite difficult, no variation. If it is linear variation, I can say that. So here it is a 0. Here just you calculate what is the shear stress, consider the average, multiply with the area. Are you getting my point? The hashed area you multiply, take the average, but it is not a linear variation, it is your parabolic variation. So how you'll do that one? How you'll do that one? Are you first of all understanding this problem? So instead of suppose someone will say that consider the shear stress distribution a linear one here, although it is not linear, consider the linear one. If someone will say like that, then what will do? Consider 0 here, calculate the shear stress here, multiply by area. Acha, somehow if someone will say that, which is not correct, the shear stress distribution across the depth is constant. 100% wrong, 100% wrong. I'm not saying anything else, but for your understanding. So across the width, if this is constant, what will do? Whatever the stress you have, just simply multiply with the average area. Sorry, area into the stress. But here it is not the problem. The problem is that stress is continuously varying from 0 to at this location. Some point is there. How you will calculate that? This is just for understanding. This I'm providing it just for your understanding. How you will calculate the total force resisted. Total force resisted, how will you calculate? So first of all, you should calculate what is the shear stress at that location, isn't it? You should calculate what is the shear stress at that calculation. Then by using that, suppose I actually don't know what is the shear stress there. What is the shear stress there at some depth? So that shear stress variation, I don't have any idea. Right? So what I'll do, I'll consider some of the section here, maybe from maybe you take some, some small strip and try to find out what is the stress at this location. What is this? Because I just now I explained, this is your depth, this is your depth, and you don't know how the stress is varying. You want to calculate the total force resisted. That is the shear stress. This is your area. Right? Are you able to understand that? So what I'm saying, that consider at some depth x what is your shear stress. Find out that shear stress at some depth x. That tau x, if you can find out, multiply with that area and integrate it from 0 to d/3. That's all. Are you getting my point? So find out what is your tx. At tx, how you will find out? VAY bar by IB, है ना? VAY bar by IB. Write it out. What is your VAY bar by IB? So V, and at some depth, maybe your width you can take at B is the width you consider, right? Although not given, B is a width. Then multiply with what? Multiply by x will give you A, है ना? Isn't it? Then multiply by y bar. What is the y bar now? If it is x and this is your d/2, so I can write down simply what? d/2 minus from here to here, the centroid of this whole area. What will be the distance? d/2 minus x/2, d/2 minus x/2, VAY bar by IB. What is the moment of inertia there? That is BDQ/12, BDQ/12 for this beam into B is B. That's all. B is B. Yes, SAY bar y by IB. Santu, absolutely correct. Now that is nothing but your tau x. That is nothing but your tau x. Is it visible to you? Now you just simplify it a little bit and that's just all. This is the variation, already you got it. Are you able to understand this? First of all, the more important is that how you are approaching to the problem. So this shear stress shear stress variation at x depth, you got it. Now that shear you just simply do some simplification. Kitna ho jayega? How much you'll get? This is 12 to 1 by 2, you take it common, some simplification, that's all. Some simplification if you do, how much you'll get it? This 12 will go up, so it will become 6 because 2 will come out, then bb will get cancelled, and v x d minus x by 1b will be there, no, 1b, and dq also will be there, dq also will be there. Now that's what I'm saying. This is your shear stress. Simply you consider, find out what is the shear force. Shear force resisted by 1/3, top 1/3. What is that? It will be nothing but integration of from 0 to d by 3 to total force you have just multiplied. Okay, just a minute. What is the force resisted by that section? First of all you write down, then you multiply. So that force resisted, how much will be force resisted by the section x? Maybe that tau x into simply your b at that section into x, that's all. Oh, dx, sorry, into dx. This is your small dx strip, how much force it is resisted by. Now you integrate it for the 1/3. So 0 to d by 3 you integrate, how much you'll be getting it here. So integration, if you'll do that, integration from 0 to d by 3, write it down all together, 6bx d minus x divided by bd cube into b into dx. Now bb will get cancelled. Simply if you integrate from 0 to d by 3, you will get 7b by 27, right? 7b by 27. This is the total force resisted by 1/3, top 1/3 of the section. The problem everywhere is about the variation. If the variation is not there, simply all whatever the average you have, average multiplied by the area. If linear variation, also average 0, and then whatever the tau at this location, 0 plus tau divided by 2 multiplied by the area. But the problem is that if you have a bk square, kahan aega? Where you will get b square? This is how one should solve. Okay, practice well, and tomorrow once again we have a session. Meet me at once again same time, that is 6:30 p.m. on YouTube with some fantastic problems. Till then, good night everyone. Good night and thank you.